Welcome everyone to the virtual classroom of PG334 Geomechanics for the spring 2020 at the Petroleum Engineering Department in UT Austin. Today we're going to talk about faults, and this is one of the first applications that we're going to see out of the topics that we have learned before. From today, we'll start applying the concepts that we have learned to real problems. And the first one is about faults. We're going to see the faults are quite important in petroleum and geosystems engineering. Sometimes they trap oil and gas. They are very important for the migration of fluids in the subsurface. And we're going to see that with variations of pressure in the reservoir, sometimes we can alter that equilibrium. So we want to make sure that we do not produce any unintended consequences from changing the pore pressure in the reservoir, for example. All right, so we will start with faults, and this is chapter number 5 in the notes, and we'll start with a brief introduction. The first question is how faults are formed. And here I'm going to make a schematic of this. Let's imagine this sedimentary system a long time ago, let's say 100 million years ago, in which we have several layers that are deposited in a sedimentary basin and for which we have an active tectonic strain, which is happening at this particular place, and the tectonic action is going to create stresses in the horizontal direction. Okay, the result of this is that if these stresses are too large compared to the vertical stress, a fault is going to be created. This is going to be the result, a fault. And that fault is going to, as time passes by, is going to result in a displacement of the formation with respect to the original location. So let me do one more layer. This was originally the fault, and now there has been a movement with respect to the original position. The result is going to be that now what is above the fault, which is called the hanging wall, is going to move relatively to the section which is underneath the fault, which is called the footwall. So this is going to be the movement that you would expect, and this was because of the action of a horizontal stress. And in this example, we're assuming that this is after a long time, so that we don't have that dinosaur anymore. But now, let's say that we have here our dear Longhorn. So this is the result. This is what basically causes faults. It's in stress, which is too high so that the rock fails in shear. And this is going to happen, as we have learned from before, when the maximum effective stress is too high compared to the minimum effective stress And this is going to depend on this friction coefficient Q, which is a function of friction angle. And for example, when the friction angle is equal to 30 degrees, this Q is about 3 times. So in this particular example, I'm going to have this type of fault whenever the horizontal stress, effective horizontal stress, is about 3 times the effective vertical stress. At that point, the stress is going to be so large that the rock is not going to be able to handle that stress and is going to fracture. That's how faults form. And in this case, this is an example of a reverse fault. If I have the minimum principal effective stress to be horizontal and the maximum effective stress to be vertical, what I would have instead is a normal fault. And this is what you see in these images. And in this case, in a normal fault, what we see is the hanging wall, which is the part of the rock which is above the fault, moving down relatively to the footwall. And the same you can see on this example on the right. I have another example to show. If you ever go to Arches National Park in Utah, when you go to the visitor center and you look across the highway, this is what you're going to see. And what type of fault would you say is that? Remember that a normal fault will be a case in which the formation moves down in the direction of gravity with respect to the footwall. And this is the case. This is a normal fault. You can see if you follow this formation, the reddish one, you can see how after a fault it's over here, after another fault is over here, after another one it continues moving and getting displaced by this fault with multiple strands. And also you can see that on this other formation, which is a little bit above the other one. So this is a very nice example of a normal fault. Actually here the Moab fault, there is a very high, a very long fault, which is about, here you see displacement of, this is about, if I remember correctly, no, this is a bush, so this should be in the order of 15 feet or so. Here in this section, there is a fault which has a fault throw, a displacement from one point relative to the other of about a mile. So this is a pretty long fault. This is a small one. But the point I'm trying to make here is that the faults are just features created by shear. We can see those very well on surface or outcrops, but now the question is, how can you look at those, or how you can identify those in the subsurface? And that's the next topic. In the subsurface, there are two ways that we can basically take a look at these faults. The first one, when we have a wellbore and we run a formation imaging tool around the wellbore to tell us how the wellbore looks like depending on ultrasonic waves or on resistivity, we get images similar to this one, in which this image is the unwrapped 360-degree version of a circular image. For example, this one starts in the north and ends in the north. When we have a wellbore that goes through a fracture like the one in the middle or through a fault, we can see that in these images as sinusoids, where the amplitude of the sinusoid tell us how steep that fault is dipping. That would be the amplitude of the sinusoid will be h, and here will be the distance, vertical distance. Well, you have it over here, from here to there, and the position of the peak and the trough of the sinusoid also tell us what is the highest position and the lowest position. That would also tell us what is the orientation of that plane with respect to the geographical coordinate system. For example, in this case, the highest point is more or less towards the east, and the lowest point is towards the west. So we know that is from this image that this particular uh, fracture is dipping towards the west. It's getting deeper towards the west because that's the lowest point. These type of images are very useful to tell us whenever we go through a fault or whenever we go to a fracture, but if we want to sample a big reservoir, it's not enough with wellbores because we're just going to sample whatever goes through the wellbore. In order to go into to image a large formation, we use seismic images. A seismic image, like the ones that we have seen before in the introduction of the course, and here I'm going to pull up one example. A seismic image like this one in 2D and in 3D let us interpret where faults are. This needs some training. The geologists are the persons which are best suited for this job. But basically, when you do not see a continuity in the impedance contrast of the layers, that's because there is a discontinuity, and this discontinuity might be a fault. In this case, you see a reverse fault. In this other case, you see here normal faults. And again, it is that discontinuity of these impedance contrast lines that tell us that there is a fault. Well, we can use these seismic images in order to create a reservoir model like the one that I have in here, in this example from the simulator. Here we have our faults, and here we have our fault planes in 3 dimensions together with some injectors and producers. We're going to see that faults are quite important in reservoir geomechanics. We want to know where they are, and we want to know what are the limit pressures that may destabilize some of these faults. So we're going to see that later on in the application part. Let's just stick with this image of a faulted reservoir by now, and we'll see how later this is useful. But again, if you want to map faults, you either use information from wellbores, information from seismic, or the best way would be that you use both and you combine those in order to obtain a reservoir model, faulted reservoir model like this one. Okay, let's talk now about what is the orientation of these faults and how we can quantify systematically this orientation in a given location. Just making sure this is recording. Yes, it is recording, so I'll continue with the lecture. These are quantities that we know as strike and dip. I'm going to jump over here to my notes to create a new example of this. Let's imagine that we have a sedimentary basin, and here I'm going to add a coordinate system which is going to help us. Oh, that's not the north. It's going to help us see the orientation of that, east and north. Let's imagine that I have a nice sedimentary system from which I'm just cutting here a block of it with very well defined layers, horizontal layers, continuous layers, and that I have now a fault that cuts through that sedimentary system. And this fault is going to be this plane, which is oriented in 3 dimensions. I'm going to erase the hanging wall of the fault, which is this section, and I'm just going to leave there the footwall, so we can see a little bit better what strike and dip are. So here now I just have the footwall. Okay, let me pass this line again, just to highlight the plane fault. All right, the first angle that we're going to define is the angle of the strike. The angle of the strike is the angle between the direction of the north, and in this case I'm going to make this line to be a line parallel to the north in my coordinate system. This is the line of the north. The strike is going to be the angle between the line of the north and the line of strike, and it's going to be denoted by an angle phi. The line of the strike is going to be the intersection between a horizontal plane and the plane of the fault. In this particular example, I'm assuming that this plane over here is a horizontal plane. So the intersection between the horizontal plane and the plane of the fault, which is this one, is going to give me the strike line. Let me change the eraser. Okay, this is the plane of the fault. Plane of the fault. And that's going to be the strike. All right, and there's going to be one more angle that we're going to define, which is the dip. The dip is going to be the angle between the line of the maximum slope of this plane, which in this particular example I'm going to make it over here. This is the direction of the dip, and this is the line of the dip, and the dip is going to be the angle between this line and the plane, the horizontal plane in this particular location. So this angle is going to be the dip, where this green line is on a horizontal plane. So for this particular example, I could say that the strike is more or less, let's say 30 degrees. Let me see if I can change this to blue just to make it a little bit more didactic. Let me try again. Okay, and what about that? No. Okay, well, just let me leave it like that. Strike angle in this particular case is more or less 30 degrees from the north towards the east. I'm going to explain in a bit this notation, and the dip angle is more or less, in this case, 50 degrees, and is dipping towards the southeast. So again, in summary, we're going to have two angles that characterize uh, a fault or a fracture, and those are strike and dip, and those are going to characterize this fault plane and are going to tell us what is its orientation in 3 dimensions. One more thing over here that I think is very nice to remember, and it helps a lot to see what the dip is. If you were to drop a droplet of water somewhere over here, that droplet of water will follow always the path of the maximum slope. So it will tend to go along the line of the dip. That's what defines the line of the dip, the path of the maximum slope. Okay, so now we know what strike and dip are, and this is going to be very useful for us to uh, quantify what is the direction of these faults and the orientation of the faults in the subsurface. And as we were seeing before, there are two ways of telling what or how to write strike and dip. For strike, we have the quadrant conversion. That here what we do is we use an angle that goes from 0 to 45 degrees, and we refer as this angle as the angle that going, for example, from the north for 45 degrees towards the east, and that would be the example for this case. But we could also tell it's from the east 45 degrees towards the north is the same thing. This is very useful in the field because in the field sometimes you're looking at the particular strike line and you have the compass in your hand, and just looking at the compass and looking at what is closer, what is the closest cardinal direction, you can tell what that angle is. And so this is very useful in the field. We can also use something which is called the azimuth convention for strike. And this one, what we do is instead of reporting an angle that goes from 0 to 45 degrees, we tell that angle as the angle that goes from 0 to 36 degrees, but we measure it from the direction of the north in direction clockwise. So for example, if I were to look at the strike of this line, I would say it is 45 degrees from the north in the clockwise direction towards this line. If I'm looking at this one, it's from the north 90, 180, 225 degrees in direction clockwise towards that line. We're going to see later on that it's not exactly the same 0.45 or 225, and that depends on the depth of the fault. But for now, let's just leave it like that, as those are equivalent. And one more thing, for the azimuth convention, you add a 0 to the angle if it's not higher than 100 degrees. So anything less than 100 degrees, you will add a 0 just to make sure that you are reporting this in the azimuth convention. And this is going to be later on very useful when we have to use the orientation of these faults to do some mathematical operations. We cannot do mathematical operations with this type of convention, but we can do it with just the angles as given by the azimuth convention. And for the dip, it's very simple. We use angles that go from 0 to 90 degrees, where 0 will be a horizontal plane, 90 degrees will be a vertical plane, and for anything in between, we'll have to tell in which direction that fault is getting deeper. For example, in the example that we just saw over here, is dipping towards the southeast. So right next to the number of tip, we put what is the direction of the tip. Okay, so now we know how we quantify the orientation of these faults in the subsurface. Let's see now how we can plot that orientation either in just a plot, as we're going to see here in these stereonet plots, or also in maps. Let's start with the stereonets. Uh, the stereonets are a way of visualizing the three-dimensional orientation of a plane in two dimensions. It sounds a little bit difficult, but believe me, it is not. So, but the objective is very simple. We have these planes oriented in three dimensions, like this one. We want to make that simpler so we can plot many of them in a two-dimensional plot, like this one. And one way of doing that is through stereonets. Let me tell you what stereonet is. A stereonet is a plot in which what you do is you plot a perpendicular line to a plane, like for example in this case this will be our fault plane. You trace a perpendicular line, and where that perpendicular line going down intersects a lower hemisphere projection, that's what we call a pole. And when we look at that pole from the top, with the top view, what we will see is a dot like this, where of course we're expecting the cardinal directions. This is the north, south, east, west, and the direction of the pole is going to tell you both the strike and the dip of a particular fault. Let me show how this works with an animation, and you can also access that in this link right here. If you click on that link, it will take you to this web page, which is an animation of a stereonet. So I'm going to make the same fault that I have over here. In this fault over here, I'm going to um, make it in this animation. So let's see. It's in a strike that is 30 degrees from the north towards the east and has a dip of, let's say, about 60 degrees. So that's going to be a dot somewhere over here. And if you notice, next, when I move the dot, there are on the second row, it says S and D, that's strike and dip. So I'm gonna get a little bit closer to here. Yeah, that's a plane. So right now I'm looking at the top view of this lower hemisphere projection. Let me make it 3D. And this is what we see. Again, this is the north, this is the south, west, north, east, south, west. And this is the plane of our fault, the line that goes from the center towards the intersection of this line with the lower hemisphere uh, is that perpendicular line. This is the pole at the intersection, and this is the pole when we look at it from the top. And let me add a few more here faults, and you do that by doing a double click. So I'm just gonna make a cloud of those, and I hope that you see by now that whenever we try to do this in three dimensions, we're gonna have a bunch of planes over here that it's very difficult to observe that in three dimensions in a single plot. So it is a lot easier to look at that as just where the poles are, because they are telling us what the strike and the dip is. Here, you see one more thing that usually we do not plot in these type of diagrams, which are the lines, which are the projection of the fault plane and the intersection of the lowest hemisphere, which are those lines. And in this web app, what you can do is you can select all of those. Let me, looks like, turn them off. Let me select those. And what I want to do is I just want to look at the pole, and here I just see those dots. Those are the poles. And if I were to have, for example, another set of faults, which is somewhere over here, then these planes will be the ones that corresponds to those. So I hope that you see that from this type of plots, you can find what is the orientation of fault and its dip and strike according to where the position of the dot is. So coming back to our schematic over here, not that one, this one, whenever we have a point in this stereonet, that's going to tell us the position of the dot, where is around this stereonet, is going to tell us what the strike line is, and is also going to tell us the dip. For example, if I were to have a vertical fracture, that would mean that this pole would intersect the lower hemisphere somewhere over here on the border of the lower hemisphere. So that would be a dot somewhere over here. If I had a horizontal plane, that would mean somewhere a dot somewhere over here, and that would be the position right there. And depending for a given tip, like for example this one, depending where this pole is moving around this stereonet, that also tells me the strike, because as I move this, the line perpendicular from the pole to the center, this perpendicular line is the line of the strike. So it takes a little bit of time to understand what these stereonet maps are, but they are very useful, and you'll see that after spending a little bit of time, it will be very easy for you to understand what the orientation of a given fault plane is with these stereonet maps. And we'll see later on that also this is very useful for recognizing the direction of stresses in a given place. All right, so this is just one way that we're going to use in order to quantify the orientation of a fault in 3 dimensions. Another way is to use geological maps. You are all familiar with contour maps. This is just one example in which we have a formation, continuous formation. Let's say this is a sand, this is the top of the reservoir. If we pass this to 2 dimensions and with contour lines, that would mean that here, this is the highest point, somewhere over there, and this one is the lowest. So I have these contour lines that go in between. So this particular formation is dipping in this direction, in direction southwest. Well, what happens when we have a discontinuity? For example, here a normal fault that makes the hanging wall to move down and the footwall to move up relative to the hanging wall. What we will see is a separation between these two layers, and actually when you see from the top, you don't see anything in the middle. So if let's say that we are mapping this sand layer here in the middle, we wouldn't see anything. And the way to put this into geological map, it will be to fill up this space with a fault line, which is this one. In this particular case, this gap is telling me that there is a normal fault. The direction of this line tells me what is the strike of this fault. In this example, it looks like more or less 60 degrees from the north towards the east, or you could also say that 30 degrees from the east towards uh, the north. And the tick, the position of the tick over here tells you in which direction the fault is tipping. So this particular fault with the tick on this side means that it's getting deeper as you move southeast. And this is the schematic that you use for a normal fault. Let me show an example of this. Here we have a map of the North Sea. So you see, here's Norway, here's the UK, Scotland, and here we have the North Sea. All these lines that we see are major faults, and these are normal faults in which we have the direction in which they are dipping with the ticks that we were mentioning before. For example, in this particular place, we know that because this fault is dipping towards the northwest, that this part is the foot wall and this one is the hanging wall. And if we go and look at this fault, we know that this one is dipping southeast and this one is the foot wall and this side is the hanging wall. So you may think, but how now? Like both of these are the hanging wall? How is that possible? And it is possible. That's what is called a graben. And we're going to see this in the next section, but let me give you a preview of that. This is what you would see. Two hanging walls, two foot walls, and in the middle the hanging wall going down relatively to the foot walls. If I were to take a cross section of this part from here to there, that would be what you're looking at from here to there. This section is the graben. And these faults are very important in petroleum engineering because, as we were saying before, faults can trap hydrocarbons, and getting to know where those faults are is very important for understanding a petroleum system and predicting what's going to happen when we change the pressure in those, as for example with production or with injection. All right, one more thing over here now related to geological maps is that with these geological maps you can also make schematics of a thrust fault. In a thrust fault, opposite to what it happens with a normal fault, you will see two sections when you look from the top overlapping on each other, and the geological symbol that you use are these triangles, where the side of the triangles also tells you in which direction this thrust fault is dipping. And another type of symbols that we use in order to tell what is the dip and what is the strike of geological features are all these symbols. For example, here, this symbol means that this particular plane has a strike which goes along the long line and a dip along the short line, and the number tells you what the dip is. Here's another example. This is the direction of strike, this is the direction of the dip, and this is the number that quantifies the dip. Here, you don't have to tell, for example, in the plot that this is a dip northeast because it's obvious from the figure itself. And this is useful because when we do not have access to 3D ways of plotting these structures, these symbols are very useful to see that in 2 dimensions. And this will be the two symbols either for a horizontal plane or for a vertical plane. In a horizontal plane, there is no strike because it's a horizontal plane. So we just use this symbol. For a vertical plane, there is a strike. The strike is the direction of the longest line. And perpendicular to that, we'll just draw a line that means that this going on both sides, meaning that that's a vertical plane. So we're going to use these symbols. They're pretty easy to remember. We're also going to use some maps that use this convention, but it's not too complicated. Remember, all I want you to remember is that the line, direction of the line tells you what the strike is. The tick tells you in which direction that particular fault is dipping. Okay, we are done with this section, and now we're going to continue with the next topic, which is the strength and the ideal orientation of faults. All right, so let me just double check that this is recording. Yes, it is recording, and we have about 20 minutes to finish this lecture. And let's get started. Well, a fault, like any other geomaterial, is going to have some strength. If you remember from that class where I had two parts of the rock which were not cemented, and then by applying a vacuum I was able to stand on top of that rock that was split in several parts. That was possible because the strength of the fault itself and because of frictional forces. And with faults it's going to be the same. Let's take a look at some of these faults that we have over here. The rock has been broken. That's why we have a fault. But they are not moving right now. They are in equilibrium. It's not that these are frictionless surfaces. They stay where they are because they are in equilibrium. And that's because the fault has some strength. If we take a look at these other pictures over here, let me get to the pictures of the faults. Right here, again, those faults are there because they have some strength. They have been displaced with time, but right now they are at equilibrium. And that's going to depend on the strength of the fault. And the strength of the fault is just going to be simply depend on the frictional properties of the fault. If you remember, we quantify that frictional strength with this parameter Q that links the maximum effective principal stress and the minimum effective principal stress. And what this equation tells us is that the maximum effective principal stress can be as large as Q times the minimum effective principal stress, where this parameter Q depends on the friction coefficient or on the friction angle. That's the same thing. And for typical values of the friction angle that go, I have a table over here, from 30 to 50 degrees, the frictional coefficient Q goes from about 3 to 7.5. 6. And what that means is that now if I make a plot, that the maximum effective stress is going to be more or less 3 times larger than the minimum effective stress. If I go over that limit, that means that I'm going over the strength of the fault itself, and that fault is going to uh, move relative to each other, or in a place where I didn't have a fault, probably now I'm going to have a fault because I'm going over the limit. It's the same thing or like what we saw before with small pieces of rock. When you go over a certain limit, the rock is going to fracture, and there are going to be fractures that divide the rock. Well, in this case, it's exactly the same, but now at a very large scale, instead of forming a small fracture, you form a large fault, and the when that happens will depend on the strength of that particular formation. And the simplified equation, in the case that we have very little cementation, is this: the maximum effective stress is Q times the minimum effective stress. All right, so let's see how we apply this to the different types of faulting regimes that we have. Normal fault, if you remember, this is the stress regime in which the maximum effective stress is vertical, the minimum is horizontal, and in this particular case, we're going to have shear failure surfaces, which are a combination of the maximum principal stress, which is vertical, and the minimum principal stress, which is horizontal. Whenever we exceed the ratio of the maximum effective vertical stress divided the minimum effective horizontal stress larger than the friction coefficient Q, we're going to have a fault or a fault displacement. And in normal faulting conditions, that will result in a normal fault. So a normal fault is going to be caused by this type of stresses in which the fault is going to be aligned with the stresses. In this particular normal fault, the hanging wall is going to move down relatively to the footwall. Uh, look at that and try to understand this makes sense because the direction of these blocks is moving and respecting the direction of the highest stress. So as this one push down on this one, the block moves down. As this one push up on this the footwall block, these ones move up. So um, this is respecting the direction of the maximum effective stress. And also it's a shear failure, so it's not going to happen, or let me rephrase this, it's going to happen at the characteristic angle that depends on the friction coefficient of the material. And in this case, the strike of this fault is perpendicular to the minimum principal stress. We'll get to see later in detail about what would be the ideal orientation of faults. For now, let me just go over the different types of faults that you will observe according to the stress regime. So in normal faulting, again, a fault is going to be created by a combination of a vertical stress and a horizontal stress. If we go to a reverse fault, like this one, then now this fault is created by the horizontal stress, which is significantly higher than the vertical stress. And when that overcomes a ratio of sigma 1 divided by sigma 3 higher than Q, that's when we have a fault slip or a creation of a new fault. And again, I'm going to explain why we have this orientation in the next topic, but and this would be, in this case, the case of the thrust fault. And last, for the strike slip fault is created under conditions in which the maximum effective stress, principal stress, is horizontal, and also the minimum principal effective stress is horizontal, so that this failure surface is going to be created as a combination of the horizontal stress, maximum horizontal stress, being significantly larger than the minimum effective uh, horizontal stress, and that creates a type of shear failure that is going to depend on the orientation of these stresses. This is not exactly a pure strike slip fault. This is an oblique fault because there is also some dip. We're going to see in the next topic that strike slip faults have a dip of 90 degrees. All right, so um, I hope that with this, now you can see what is the origin of the names for the faulting regime or the stress regime in several places. When we started this class, we started with the classification of the stress regimes, normal, strike slip, and reverse, but probably you didn't know why or where the name of those stress regimes came from. Well, now we know. It's associated with the types of faults that you would observe on those places. And probably we go now to this map. Now this will make a lot more of sense to you. Let me zoom up here in the lower part. Uh, Here we have the different types of stress regimes associated with the faults that you would expect and those conditions. So here you have maps of different places with the expected stress regime at that particular location and what that will mean for faulting. For normal faulting in red, strike slip in green, or thrust in reverse faulting. If you go to some regions, like for example, have a lot of thrust faulting and mountain building, that will be Himalayas here, the Andes over here, some of the Sierras in California, some of the Rockies. Also, you can see that affected by, um, in this case, strike slip and also thrust faulting is more evident here in the Appalachians. The line of the Appalachians, you see a combination of those stress regimes. All right, so something very important that we should also remember is the concept of a paleo stress. Now that we know how faults form and how they are affected by the orientation of stresses, we may be tempted to use that information in order to tell what the current stress regime is at a particular location. For example, if I look at this fault right here, uh, what would you say the type of fault it is? The hanging wall is moving down relatively to the footwall, and the dip of the fault is also relatively steep, and that's going to be associated with a normal fault. One more thing that I like to say over here is that usually for normal faults, you would expect the hanging wall, which is above the fault, to move in the direction of gravity, moving down. In a reverse fault, you see the opposite. You see the hanging wall moving up, opposite to gravity. In this case, this is a normal fault. So in this case, you might be tempted saying, oh, okay, I know this is a normal fault, so I'm pretty sure that right now in this place, there should be normal faulting regime. Well, that might not be quite true because the stress regime that caused this particular fault, we know that it was normal at the time that it was created, but we don't know if after all the time that passed between the fault was created and today, if the stress regime is the same as the one that it was before. And that it may not be necessarily the same. The stress regime may have changed, may have gone from normal faulting to reverse or to strike slip, or it may be still normal faulting, but uh, it may have an orientation of the minimum horizontal stress different, let's say not in east-west direction, but now in north-south direction. So it's very important that you remember that the current orientation of faults doesn't tell you what the current stress regime is. It tells you what is the stress regime that caused that particular fault. But today, it might be different to what uh, it caused that fault to begin with. All right, um, let me come back here the to the notes, and we are going to finish the lecture with this topic today. I like that you take a quiz, which I'm going to upload on Canvas. I want to make sure that you all follow the lectures, and at the time that we get to the exam, you are all prepared. Remember that I'm going to hold office hours through Zoom at 4 p.m. Tomorrow Tuesday and every Tuesday, so you can find me there. You can also send me an email. I'm available. I'm working every week, Monday to Friday, and sometimes more. So just send me an email, and I'll try to help you with everything you might need. So, starting on Thursday, we'll talk a little bit more about what is the ideal orientation of faults and how we can use that to interpret the stress regime that cause those particular faults. You will see that that's something very important, and it will allow us to understand geomechanics a lot better. Okay? Okay. I'll upload a new video on Thursday. Goodbye.